10 minutes break at 10 to 10 as usual, and all the questions will be answered 10 minutes before the end of the lecture. So please turn off your microphones and cameras, and then, because the lecture will start shortly. In this case, whenever you are ready.
All right. So thanks for attending the last lectures of mine. And then, of course, Matthias Erhard will continue in the afternoon. I will have two more lectures, and I decided to do the first one a little differently from what I had before. I want to talk about the valuation of electricity storage contracts. And the reason is I want to show one application with the cost method and one application more with neural networks, that is the CVA application. But I thought it was nice also to finish with an application of the cost method, and then electricity storage contracts are maybe an interesting topic in which we can review a little bit of what we did regarding the cost method in the lecture so far. So the contents of the presentation, I'd like to say something about the relevance of electricity storage. I'll say something about the electricity market. Then we have a pricing model for the electricity price, and that's a polynomial model, a so-called polynomial process. And I will be brief about the polynomial process. I'll say something about options and the electricity storage contract. Then we do it with the cost method, and I show some numerical results. And why did I decide to do this? Well, I think it's nice to see for a polynomial process how we work with the cost method regarding the characteristic function. And also the contract, the electricity storage contract, it's just a little different from what we have seen so far. So I think that is interesting. Okay, why is electricity storage relevant? Well, first of all, we know that, for example, the European Union has agreed to reduce the greenhouse gas emission. And so the 1990 level is like here, by 2017 there should have been a reduction of 21%. Then by 2030 there should be a reduction of 40%, and by 2050 there should be a reduction of in one scenario 80%, and in the other scenario 95%. So we have to move to renewable and green energy. And now, of course, the definition of green energy changes already a little bit, but still, there is a difficulty that renewable energy, in terms of wind and solar energy, it's difficult to store it. So one works on electricity storage, and storage of these renewables. That is one of the possibilities to match with the targets that are set for the future. So to meet the targets, we see a growth of renewable energy sources like solar and wind energy, right? And then they cause an increase in uncertainty, because when the wind doesn't blow, we have to do something, and there's a variability in the supply of the energy. And one of the solutions for all these uncertainties is considered to be electricity storage. So that is, you store electricity when there's too much supply, and you return electricity to the grid when there's a lot of demand. And nowadays, this is also increasingly interesting from a financial point of view. So we want to look at one such contract and see what we can do by storing and by returning. Is there a financial benefit, or does it make sense to do a financial consideration? Because as we know, when there is a potential benefit, that also enhances and increases the improvement of the materials and of all the investments in maintenance or in manufacturing, etc., and research and development. Well, the electricity market, well, many countries have released their electricity prices, so there's a liberalization, And electricity is nowadays also considered a commodity, like oil, gas, but also like many other commodities. There are exchanges that trade electricity options like APX. However, electricity is a little different from other commodities that I've just mentioned. It cannot yet be stored in big amounts, and therefore prices respond more extremely to supply and demand and to external events like a shortage of coal or weather conditions. We typically see them back in the prices. And these impacts, the impacts of external events, that even increases with the transition to renewable energy. Well, here we see a picture of the daily prices, the daily market spot electricity prices from September 2019 up until July 2020, August 2020. We have the gas price in blue, and we have the power price in red, and you see that the power prices are clearly more spiky, more volatile, more spiky. So the features that we see in electricity prices that are high volatility, extreme price spikes, sometimes around Christmas, everybody, or some other day, everybody has a lot of use of electricity, or around extreme cold days or warm days, if we think of air conditioning. And we see a mean reversion, right? The price reverts back to its mean quite often. So we see mean reversion, extreme price spikes, and high volatility. And one of the suggestions in the current research literature is to use a stochastic, a polynomial process, to consider the electricity price as a polynomial function of another process. That is a polynomial model. Filipovic from APFL is one of the leading researchers in this direction. Tony Ware from Calgary is another one. So the polynomial model is nowadays considered and also studied heavily from a theoretical point of view, but also from a practical point of view. So we also thought, let's use this polynomial process. So psi here, in this case, psi is an increasing polynomial function. Psi of x is the sum, n runs from 0 to n, pn xt to the n. So it is a function, so h in this case, h of p, where h is like 1x, x squared, x to the n. It's really a polynomial process. It's a vector of basis functions. P hat is the coefficient, P bar is the coefficient vector, and X then typically follows a polynomial process. And polynomial processes, well, we can do a whole lecture about those, but I'm not willing to do that. So I just point you to the Filipovic work and familiar polynomial processes. So the basis for our polynomial familiar processes are like geometric Brownian motion, the Cox-Ingersoll-Ross process, and the Ornstein-Uhlenbeck process. And typically, if we think of mean reversion in our electricity prices, we may end up with the Ornstein-Uhlenbeck process. Well, why do we use polynomials of such a process? Well, we can mimic these outliers better. If we work with polynomial processes, we can calibrate this to some of the features that are observed in the electricity market. So the polynomial model for electricity prices, the conditional expectation phi of xt given xs, that can be found without a density function or without a characteristic function. The solution is a polynomial of x, which preserves the degree of the original polynomial. So we have a moments formula in a polynomial process for little s less or equal to little t. It holds that this conditional expectation is in fact this H matrix, H which depends on xs, times e to the power g t minus s times this p bar. And g is the matrix representation of the infinitesimal generator calligraph G of X. So we have the moment generating function, but typically we don't have the density of a polynomial process, neither we have the characteristic function. And that is, of course, for us a challenge, because we have clearly mentioned that we need a characteristic function to work with the cost method. So that, for us, that was one of the research purposes for adopting such a model. So the time t price of an electricity forward, where the electricity is directly delivered at a future time capital T, that is given by such a conditional expectation, the conditional expectation that we have just seen. So for many of these prices, in the classical pricing methodology, we don't need a characteristic function or a density. We just need to have access to this conditional expectation. So that is one of the reasons why this got adopted already. But as mentioned, in our case, we would like to make use of a characteristic function. And how do we do that? So how do we simply write this down in a sketch? So suppose we have the Ornstein-Uhlenbeck process, dxt is kappa theta minus xt dt plus sigma dwt, and that is the underlying process. You may see it here. It is an Ornstein-Uhlenbeck process. It has a certain volatility, which is visualized by the wiggliness, and it has a certain a mean reversion, and you see something like a mean reversion appearing in this picture. So that's the original process. Then we use it inside the polynomial, p3x to the 3 plus p2x to the 2 plus p1x, a third order or a second order polynomial, something like that. And the polynomial would look like this. And together, so see the scale here, the scale goes from 1.4 to 2.4. And in order to generate these outliers, we use this polynomial map, because that makes that our polynomial process then goes from 10 all the way up to 40 even sometimes. With a peak, it goes up to 40. So by stretching somehow this process by means of a polynomial, we can mimic some of the features that we see in the electricity market. So that is the setting, and that is the setting. That is the reason to look at the polynomial process. And for example, these coefficients could be calibrated, and also kappa and theta, they could be calibrated, and sigma as well. Now let's have a very short recap because we need to go to the electricity storage contract, and then I'll bring you there from the European to the Bermudan option to the Bermuda next to the Bermudan option with multiple exercise rights. Well, of course, we have a T0 here, a final time, maturity time, capital T here, and we have only one exercise moment in the case of a European option. We can only exercise here, and then we get for a call the maximum of ST minus K and 0, and for a put the maximum of K minus ST and 0. Now, in the case of a Bermudan option, we have these discrete exercise dates, T1, T2, T3, and T4 here denoted schematically. The Bermudan option, as you remember, it gives the holder the right to exercise the option at a certain predefined finite set of exercise moments. So at every exercise moment, I've shown you this in the slides of Tuesday, in fact. At every exercise moment, the holder of the option must make the decision to exercise or to continue. Exercising is at some time Tm, at some stock value Stm, you get the maximum of K minus Stm in the case of a Bermudan option. And continuation implies you look at the discounted, just for a time step delta t, you look at the discounted value e to the power minus r delta t, of the expected value of the option value at a new time point under the risk neutral measure, given that we are now and we have our knowledge up to TM. And then the holder will make the decision we had. So the writer thinks the holder will make the decision which results in the highest value. So the value of the option at time Tm is the maximum of exercising and continuing. And then these can be, now we go to the multiple exercise rights. So the holder of a Bermudan option with multiple exercise rights, that is not so much an option which exists, but it is, well, it does exist, but it's more exotic, but it is a stepping stone towards these electricity options. So now we say the holder has the right to exercise the option multiple times at a predetermined finite set of exercise moments. And the number of rights to exercise before expiry, that is denoted by R. There are R rights. So when R is 2, it could be here and here, that there is the opportunity to exercise both at both places. There's multiple rights, or it could be here and here. You can, or even differently, there are 2 rights in this set of time points at which the holder may exercise, and yeah, when the rights are gone, then it is done, basically. Multiple exercise rights. So the contract doesn't end when one exercise right is actually exercised. Only when our exercise rights are exercised, then the contract ends. So basically, if we look at a specific time point, so we always try to find, we want to come up with a cost methodology, or basically with a dynamic programming formulation, we would like to come up, because we can work with that, and we can even use Monte Carlo with that. So at each exercise moment with J rights left, suppose we have J rights to exercise left, then the holder must make a decision. The decision is either you exercise and you continue with 1 right less, and that gives you the value exercising plus continuation with 1 right less, yeah? Or you continue with the same number of rights left, and that gives you just a continuation with J rights. It's one of these 2, and typically, again, the exercise is just as we noticed, but continuation with J rights left basically means you look at the discounted expected value under the measure Q of the option value with J rights left. Yeah, the option value at a new time with still J rights left. All right, so that is, and the details, and the paper has just been released about the electricity options, but the details are also in the master thesis. There's an MSc thesis of my co-author Boris Boonstra. At that time, it was still at the Delft University of Technology. But the idea is clear, right? The idea is either you exercise and you have 1 right less, or you do not exercise and you keep all your rights. And then you have a specific formula for a continuation value with J rights left. So what we do, the option value at time Tm, the option value at time Tm with J rights at Tm is the maximum of exercising plus J minus 1 rights left, or not exercising and continuing with J rights. Now let's look at these electricity storage contracts. Then, for example, the holder, in one of these contracts, you have the right as a utility. For example, you have the right to either store electricity or to release electricity from a storage facility. So the holder has the right to change the electricity level in the storage by buying or selling electricity at a predefined finite set of exercise moments before expiry. So at each time in the future, the utility owner or the holder of this electricity storage contract, it's a financial contract, has the opportunity to either buy electricity or to sell electricity from the storage. Of course, there are constraints, right? So when we're dealing with an electricity storage, we have additional features. And they make it interesting, I think. That's nice. We have physical characteristics of an electricity storage, the capacity, the efficiency, and the endurance, right? We have operational constraints like the maximum charge and discharge rates. And we have the possibility to have a negative payoff, because when we withdraw electricity, we would have a negative payoff. And we can either buy electricity or sell electricity. And there is a settlement date here, a settlement date, an extra date. The contract ends at T4, at capital T here, but we have a settlement date in our system. And at the settlement date, the holder would receive a penalty if she does not comply with the contract conditions, denoted by QS. For example, when there's not enough electricity in storage, or when it's not empty, for example, or when there's not enough in storage, there is a penalty to pay. And that penalty, we have made a settlement date in order to execute that penalty. And that penalty also plays a role in the decision to buy and sell electricity, right? You could imagine when you are here, you need to make a decision. You could get a penalty if you do not have sufficient electricity in storage. It may be more beneficial to buy extra electricity because you want to avoid that penalty at the settlement date. And that is also how it happens in practice. So how do we formalize such a contract? Here we see our battery. And we have an E min, electricity level min, and an E max, an electricity level max. And we have these delta units of electricity, E max minus E min divided by NE. So we discretize the electricity storage capacity into NE energy levels. Now at each exercise moment, with E at Tm electricity in storage, the holder of the contract can choose an action delta E. But the holder should take into account operational constraints and physical limitations. So delta E should lie in an operating limit. Yeah, so it should be somewhere between I minus and I max. You cannot have too much. You cannot insert too much in a storage. You cannot release too much. So these are operating constraints. And also the total number, the total energy, E at Tm plus delta E, it should lie within limits E min and E max, right? We cannot exceed the storage, and we cannot have less than a minimum amount of storage. So we have these constraints that we should satisfy. The operating limit says something like it should be in this range. And then we have charging and discharging an electricity storage too quickly. That will reduce the lifetime of the storage. So therefore, we set actions on which the storage can last as long as possible. So delta E should be within some limits. Delta E should also be within some other limits. And these are the limits for sustainability of the storage. Yeah. And otherwise, we would have a penalty. So we have these operating limits, but moreover, we also have charging, discharging limits. And otherwise, we would get a penalty. So in fact, we allow, for example, only the amount of energy to change in such a green part. Now, what about the electricity, the efficiency? The efficiency is very important because when you buy and you sell and you lose something because of the efficiency. You may not get 100% of your electricity bought and that can be released. So there's an efficiency of a storage. And of course, that improves all the time nowadays. And there's a lot of investment in research and development in this area. So this efficiency improves, but the current electricity storages are between 60 and 95%. So therefore we say we take a payoff function, the payoff, and the payoff is connected to releasing storage and purchasing releasing electricity and purchasing. And we say that when we buy electricity, we take that efficiency into account. So then we have something like minus S divided by eta times delta E. Yeah. And when we do nothing, of course, there is no change, there's no payoff. And when we release storage, when we release and we sell, then we have minus STM times delta E. And delta E is negative, so that is a positive revenue, and this is a payment to be made. So with this eta, this implies that 1 over eta greater than 1 units of energy need to be bought in order to sell 1 unit of energy, right? So you can imagine that the price should, when it's only 60%, you can imagine the price should change drastically in order for this to be beneficial. But if it's 95%, it may be different. And when this will become 100% in the near future, then of course also this scheme will give some different results. So at every exercise moment, at every time that the electricity utility has the right to do something, we have E energy in storage, then the holder of the contract has to make a decision which allowed action delta E to take. So we'll choose the action delta E, which results in the highest value. So the value of the contract is the maximum over delta E of exercising G at TM STM delta E with different delta E's, plus continuing with E plus delta E, plus the penalty. So you look at the maximum E for the combination of buying delta and delta can be delta can also be 0. It can be negative, can be positive. So we maximize over delta E the revenues, the continuation value, and the penalty. Yeah. So the continuation for E plus delta E energy units is the discounted expectation under the measure Q of the value of the option at the later time with the same number of energy units. So you see, slowly you see the Bermudan option features appearing, right? Multiple exercise rights, just the Bermudan option with 1 exercise right. You see it appear back in this system. Of course, we have a maximum over delta E. We have constraints taken into account. It is something like a real option. You are really looking at a physical problem and you're trying to make a financial problem out of it. It's pretty nice. And we use the cost method, as you could imagine, in a research environment. And the cost method, well, just a reminder, a quick reminder, it's a numerical integration technique. It approximates the risk-neutral valuation function, so V at time t0, and for some variable x. I told you we use x, we use S0, but in principle x can be any function. Can be any function, f is not a good, any function of st or S0. Discounted expectation under the risk-neutral measure of the value function at time t1 with as variable y, a function of st1. Yeah, this is a function of st1. And if we write that out again, that's the e to the power minus r delta t, the integral from minus infinity to infinity, v at t1. So v, the value of the option at t1, with our unknown y times the transitional probability density function dy. Now, as I have mentioned, and which appears to be very important in this context of the polynomial processes, is that x and y can be any function of the asset price st0 and st1. Particularly in our case, we make it x will be psi inverse of st0, and that is xt0. And y is psi inverse of st1, and that is xt1. Why is this important? Well, for the polynomial process, psi of s, we don't have a characteristic function. Sorry. S is psi of x, right? That is the polynomial process. Psi of x is s. For s itself, we don't have the characteristic function available. For a polynomial of a stochastic process, we typically do not have the characteristic function. It's not an affine diffusion, for example. It's not Levi-Kinshine. But as we can have any variable here, we can take, for example, psi inverse s, and that gives us x. Yeah, and x, as I mentioned, that was an Ornstein-Uhlenbeck process, or a normal process, or something, a CIR process, something for which we have a characteristic function available. So we adopt an x, in our case, the OU process. We choose for an x process for which we have a characteristic function available. And then x is just the inverse of psi times s, and y is the inverse of psi times s at t1. So how was cos again? A quick reminder. We start from the risk neutral valuation formula. We truncate the infinite domain. We make it an integral from a to b. Then we will replace the transitional density function. We will replace it by its Fourier-cosine expansion, a sum. K runs from 0 to infinity of some coefficient, payoff coefficient, option coefficient times cosine, with a dash here, because the first term is multiplied by 1/2. And we truncate that. So we have n minus 1. So we have n terms in total. And that is the cos method, where a, k is then f times the cosine. And the f times the cosine is replaced by the real part. That's in the next slide, I hope. Yeah, it's replaced by the real part of the characteristic function with a specific argument times a complex exponential. We substitute this in the Fourier-cosine expansion. We look carefully, we use Fubini, and we look carefully and we see that our payoff coefficients, they look like this. And when we have a European option, we have analytic form for this. And we called it H in the previous one, but we call so many things H, so I decided to call it capital V here, over here. So this is known in European case, it has a closed form solution, and therefore this is so convenient. With a polynomial model, it then looks as follows. S is psi of x, so it is like, here it's a second order polynomial, 1 minus c over 2 x squared plus cx. It's something like a new constant times x squared plus another constant times x. The underlying process is an OU process. And then we use the cos formula, right? And I want to show you this. Yeah. If we do this, then we could have x is st and y is s of capital T, but then we would need a characteristic function for x, and we would need a characteristic function for y, and we don't have it because that is this function. Now, if we make the transformation, x is psi inverse s, which is x little t, and this is x capital T, Then we have again still this payoff with the y here. And now we have psi of y here. In fact, in the payoff, it says psi of y because it has to be s. And what we can do now here is we can use the characteristic function of the Ornstein-Uhlenbeck process. We have x here as the primary unknown. So we have v of t0 and x. And that is then, if we work that out, it's the real part of that characteristic function of the process inside the polynomial model times this complex exponential times these option coefficients. And these option coefficients, they then have psi y inside and then dy. So now it is all related to that Ornstein-Uhlenbeck process for which we have a characteristic function. So that works. In the case of Bermudan option, well, I just go very briefly because you remember we had this maximum of G and C. C is this discounted expectation. So here we have the cost formula for the continuation at time Tm-1. It is like the discounted sum of n terms of the real part of the Ornstein-Uhlenbeck function times the complex exponential times the option coefficients. And these option coefficients, they are connected to the maximum of exercising and continuing times the cosine. And this is, we split it in two pieces with an x star. In one piece, we exercise, and in the other piece, we continue. And these two functions, capital G and capital C, they can be computed highly efficiently because these are just the payoff coefficients and these are the continuation coefficients. We write it out carefully. We substitute for C, we substitute that discounting of the previous option, and recursively we get to our option coefficients. Multiple exercise rights. Then remember the value of the option with J exercise rights is the maximum of exercising plus continuing with J minus 1 exercise rights and not exercising and keeping J exercise rights. So also here we will look at the maximum of these two, exercising and J exercise rights, J minus 1 exercise rights and J exercise rights times a cosine. And we can also work that out with a capital G, a capital C with J minus 1 exercise rights, and a capital C with J exercise rights. The electricity storage contract, that is what we are doing it for. So then we have at final time, we have the penalty. If we don't satisfy the constraints, QS is a penalty. So at the settlement date, M+1, we have the penalty. And we can also put that, of course, in a payoff function, right? So that is 2 divided by b minus a, the integral from a to b of that penalty function times the cosine dy. At any time prior to that settlement date, we look for the maximum of delta E of exercising delta E, of buying or selling delta E units, and continuing with E plus delta E units, and the internal penalty if we don't satisfy the internal constraints. We get a penalty if we release, if we do not satisfy certain constraints. And the continuation is then, of course, the discounted value of the continuation with E energy level is the discounted value of the expectation under the measure Q of the option value at a later time, also with E levels of energy. So that's a lot. I want to show you this because it's quite heavy in computation, right? But it's interesting. So we look for these option coefficients in case of the electricity storage contract. 2 over b minus a, the integral from a to b of v. And v was the maximum over delta E of exercising, of doing something with delta E units, continuing with E plus delta E units, and the penalty, internal penalty. And now we have to look for multiple, we look for all these delta E's. These are many delta E's. We can have 2 units, we can release 2 units, we can have 3 units, 4 units, whatever stays within our limitations. And for each of those, we look at the maximum value. So we split, like we split it in the case of the Bermudan option, we split it between exercising and continuing. Here we split between 0 units, E0 units, E1 unit, up to En units. So we make the integral, we split the integral into an integral from a to x1, from x1 to x2, etc., until xn to b. And for each of them, we look at the maximum, at the value of delta E, which is still the value at which we have a transition from delta E n minus 1 unit to delta E n units. It looks a bit complicated, but I hope you get the impression, you get the insight of what we are doing. We are just generalizing the Bermudan option case to multiple exercise to electricity contract. And then we end up with a sum of terms. So I runs from 0 to n of all these payoffs with delta EI units, all these continuations with E plus delta EI units, and this penalty, this internal penalty with delta EI units. If we satisfy the constraints, of course, this penalty will be 0. If we do not satisfy the constraints, but we make a lot of revenue, then again, it could be that we violate the constraint and still take the revenue. We look for the maximum. Now let's show some numerical results to finalize this piece. We look for with a second order polynomial. We have an underlying Ornstein-Uhlenbeck process, and we have some parameters, little c, 1/2, kappa 0.3, theta 11, x0 is 10, t is equal to 1, and there are 50 opportunities to make a decision. We analyze 2 volatility parameters, 0.3, which is low volatility, and 0.9, which is a high volatility. And we see that then in 1 year, the prices fluctuate quite drastically from 30 all the way to 37 and all the way down to possibly 22. And when the volatility is relatively low, 0.3, the price doesn't fluctuate that much. In financial option pricing, you may think that 0.3 for a volatility is already high, and that's true, right? We know that in financial option pricing, a volatility of 0.15 is nowadays standard, or maybe 0.18, and high is already 0.25. But the electricity market is a different market. The commodity market is a different market with different features. And this is considered a low volatility there, and this is considered a high volatility. And then we have 2 contracts, the contract, two contracts in this presentation, but we have more contracts in the paper. So I will refer you to the paper. We have a start energy level, E at T0, it's 7 megawatt hour. A minimum capacity is 0. A maximum capacity of this storage unit is 15. The minimum change is -6. The maximum level change is +6. The minimum energy level without penalty is -4. And the maximum energy level without penalty is +4. So we can move between -6 and 6, but if we are from -4 to -6 or from 4 to 6, we can do that, but we get a penalty. And the penalty of discharging too rapidly is -3 euros. And the efficiency of the battery is in contract 1, it is 95%. And the penalty at the settlement date, so if the energy level at Tm plus 1 is less than the energy level at the initial time, then you get a penalty, and the penalty is 350 euros. And the contract 2 is essentially the same, but it is a highly efficient storage. So eta, the efficiency rate is 100%, and all the other characteristics are the same as in contract 1. Now, what are the contract values? Well, for the cost method, well, with a low volatility and a 95% efficiency, the contract is worth nothing. Nothing happens essentially. Yeah, it doesn't pay off to buy and sell electricity. And when we are dealing with a highly variable electricity market, sigma is 0.9, then the value it's worth something, but not that much, right? It's only 1 cent or something that this contract is worth. So we see that for sigma is 0.3, nothing happens. Yeah. This is the average energy level. It stays at 7, and the utility is not buying or selling, or we don't advise the utility to buy or sell. Here at 0.9, also the bulk, the average of the strategies is also do nothing. There's one that in the beginning starts to buy a lot and then in the end sells a lot, and there's maybe one that also does the other thing and even takes the penalty for granted, but in the bulk of the strategies is to do nothing. So when the energy efficiency is not 100%, it's very difficult to make a profit by buying and selling. So let's now look at 100%. This is an efficiency of 100%. Hopefully that becomes true in the future. And then we see that our contract has some value. For the low volatility, it has some value. And for the higher volatility, it has some more value. And I also wanted to say, we also do a Monte Carlo simulation that is also possible with a 95% confidence interval. And our values with the cost method are indeed within the confidence interval. So this gives some confidence. And there's even more confidence of the quality of the solution method in the paper. Well, what do we see? We see that we start off. So this is the strategy that is then advocated. The bulk of the strategies first buys electricity and then releases electricity up until some part, until we have to buy electricity again in order to not violate the penalty, not get the penalty, not violate the constraint. And the same, more or less the same, we see for a higher volatility. We first buy, and we have some uncertainty, and we have a 95% confidence interval. We are always in the 95% confidence interval. We have this. And in some of the scenarios, apparently the maximum is taken and also the minimum is taken. But in the bulk, it's first buying and then releasing energy. So that's interesting. We have an optimal control. We have the energy level. We have the optimal control is delta E. And with that, we can also use the cost method in a fancy way in order to do these contracts. And we get numbers because it's just integration, and Longstaff-Schwarz or a Monte Carlo method gets confidence intervals. And specifically when you do both, a Monte Carlo setting and a cost setting, and you get the very similar solutions, you can have confidence in your methodology, in your solution method. And in the paper, we also have the car park as a power plant. So we have a power plant, we have a car park full of electrical vehicles, and the utility may decide to release energy at night, for example, or to store energy in a huge car park. And then see if, of course, at the end of the day, a constraint has to be met. You really want the cars to be able to drive again at the beginning of the day. But in the nighttime, there can be a strategy to release energy and to buy and sell energy in order to facilitate a surplus of energy, for example. We can see the car park as a storage facility. And the details of this are worked out in the paper. All right. That concludes my first talk. So again, as I told you, I wanted to show you a nice application of the cost method, a recent one, and it resulted in a paper. It's just been released in Applied Mathematics and Computation, Applied Mathematics and Computation. And if you're interested in this, just send me a mail. I can send you the paper. It's also on archive, of course. And then these are the valuation techniques for financial derivatives. We have seen what we should do with the cost method when we have power prices following a polynomial process. We formalize the contract for storing electricity by trading on the electricity market, allowing the contract to be valued efficiently. And we examined various electricity storage systems and efficiencies, like also the car park as a power plant, and that is in the corresponding paper. So I thank you for your attention for this first part. Okay. Okay, welcome back. So this is the last piece, and I wanted to sketch another research line that we are currently doing. So you have seen it. One of the bigger research line in my group is the cost method for various products. So I have given you a glimpse on day one and a little bit on day two and also now. And the other bigger thing is simulation, essentially, and simulation slowly moving into financial practice. And here we are nowadays very interested in the neural networks. So I also wanted to show you something of that. And this is work with my current PhD student, Christopher Anderson. And it is about learning exposure profiles for portfolios of exotic derivatives. So many researchers look at CVA, but for one derivative only, or in a controlled setting. And we try to go to a portfolio of derivatives and a high dimensional setting. So slowly moving towards practical relevant applications. The table of contents for this last presentation. I'll give some background, then I'll show the neural network algorithm, and it consists of two phases, as you see, a phase 1 and a phase 2. So we learn stopping policies, and later we will learn portfolio exposures, and I'll show some numerical experiments after that. So what is exposure? We have seen it already on Tuesday, right? We have discussed a little bit the concept of CVA, of credit value adjustment, and all the time we look at the exposure of an investment to a counterparty. How much does the counterparty owes us? So how much would we lose when the counterparty would go in default? The exposure is something like the amount of money that is lost when the counterparty goes in default. So the amount an investor stands to lose if the counterparty defaults. And there are basically two notions, the netted notion of the netted exposure and the regular exposure. And this is a portfolio of J derivatives. So we have capital J derivatives, and we look at the sum of these J derivatives and the maximum of the value of the derivative and zero. And we look only at the exposure to the counterparty that hurts us here. So ET, the exposure at time t, is the sum of the J derivatives of the maximum and zero. And then there's a netted exposure. And the netted exposure has the maximum outside the sum, as you see. We first look at all the exposures with the counterparty. They can be positive, they can be negative. So we are netting them. Sometimes we owe the counterparty. Other instances, the counterparty owes us. We combine all of them, and then take the maximum. And that is the netted exposure. And it's clear that here there can be negative exposure. So this is typically less or equal to this one. And then the distributions of the netted exposure over time, and the exposure, the regular exposure, these are the exposure profiles. And one of the challenges is that portfolio of J derivatives. right? That is one of the challenges that we are dealing with here. And this exposure plays a role in many of the valuation adjustments. As I mentioned, we learn in university, we learn to compute the fair value of the option, but we do not take the default possibilities of a counterparty into account. And that gives us a CVA, a credit value adjustment, and it gives us a DVA, a debit value adjustment, a funding value adjustment, a capital value adjustment. There are many of these letters collectively referred to XVA, but in any of them, here's the loss given default, here is the funding, and here is a risk-weighted asset. So there's all sorts of quantities, but the exposure is always there. So the exposure plays a central role in any of these adjustments. I don't want to go in detail into any of these adjustments. This is a numerical session, so I will only talk about the exposure computation. So in general, we do not have access to the distribution of the exposure. However, in special cases, we can draw random samples. The exposure at a path, omega t, runs from 0 to capital T, and that would be distributed exactly as S. However, in most cases, the best we can do is to draw samples from a distribution, which is in some sense close to E. So the distribution of the exposure is approximated by its empirical counterpart. And the common measures we are dealing with, as we have seen on Tuesday already, are the expected exposure, the expected value of the exposure, and the potential future exposure. That is like a quantile. It's a quantile, and it can be either under the measure Q or under some measure A, which can be either the real world measure or some back testing, stress testing scenario, something like this. But we look at how much on average are we exposed and how much a mass is in the tail regarding the exposures. Now, in a simple case, we can do everything analytically. Hence, if you think of a single European call option, so capital J is equal to 1 in this case, and we work under Black-Scholes dynamics, so then ST is equal to S0 e to the power R minus 1/2 sigma squared T minus T plus sigma times omega. And we have the payoff at final time, the maximum of ST minus K and 0. And then the option value is well known, of course. It is the Black-Scholes option value with the normal distributions here. And the arguments D1 and D2 that are given by this. So we know everything. And then we can sample exactly from the exposure of the Black-Scholes. So the exposure of Black-Scholes over time T, it is the maximum of V and 0. And because an option is, of course, non-negative, this is in fact the option value at any time T and S. So in this case, it's easy to get to work with the exposure, but this is of course an exception, right? Now let's look at an example, and let's look at an example of a portfolio consisting of 3 financial derivatives, 1 European future and 2 American options. And all contracts are initialized at time t0 and they mature at time capital T, and they depend on the same risk factor X. Now let's assume that at some time little t, in 0t, and given that xt is equal to x, we have the following intrinsic values. The value of the future is minus 10. The value of the first American option is plus 10. And the value of the second American option is also plus 10. And we would know that at this time little t, the immediate payoff of the American options would satisfy the payoff for the American option. It should be an H, right? It should all be an H, and this should be a little v. This is a little v. Then the immediate payoff would be less than 10, and the immediate payoff of the second American option would also be less than 10. suppose we know this. This is the setting now. We have -10, we have +10 and +10. And if we would exercise, we would get less than 10. If we would exercise the second one, we would get less to 10. So in the risk-free environment, when there's no default, then we would not exercise our American options. And what we have in our hands, 10, is more than what we would get if we exercise. So it's better to keep the option, right? If we look at the conditional expectation, it may be wise to keep the option at this time, little t. Now this changes, of course, when the counterparty could go in default, right? If the counterparty could go into default, we could potentially lose all of this money. So in the case of a defaultable counterparty, the situation changes. So let's remember -10 for the future, 10 for the American option 1 and 10 for the American option 2, and the exercise is less than 10. Now we have a table and see what happens. So let's look at the exposure to the counterparty given different exercise decisions at time t, with and without the netting. Yeah. So without netting, what we would lose if the counterparty would go in default is 20. Because it's the 2 American options. There's no netting, so we don't look at the -10. So there's the 2 American options, we would lose 20. With netting, we can look at all our exposures to the counterparty. It's 10 plus 10 minus 10, which would be 10. Now, the exposure, if we would exercise one of the American options, the exposure would be only the other American option, so that would be 10 without netting. And with netting, it would be 0 because we would only have the future and we would have the remaining American option. And if we would exercise both American options, we would have without netting 0 and 0 exposure. And with netting, we would also have 0 exposure. So when the counterparty is in severe financial distress, it's likely to exercise both American options if there is no netting. And one of them in the case of a netting agreement, right? Because then you get rid of your exposure and here you also get rid of your exposure. Now, this is a very simple example, but we see 2 things quite clearly. First of all, the exercise decisions for these American options, they are affected not only by the risky counterparty, but also whether or not we have a netting agreement. And with netting is different than without netting. And also, moreover, in the presence of netting, we cannot only make a decision for one derivative in isolation, but we should look for all the American options simultaneously, right? If we would look at one derivative, we would exercise maybe both of them, but that's not necessary. We could also exercise just one of them, and also have all the exposure disappear. So these are 2 interesting things. If we deal with portfolios, we should look at the whole portfolio in order to make decisions, especially in the case of netting. And this is sort of interesting because in banks, all these derivatives are traded in different groups, right? There is an FX counter, there is another counter. All these counters have their own decisions, but here we say it should be a holistic approach, right? You should look at the whole portfolio and make a decision on the whole portfolio. It makes sense. Now, how do we approximate a distribution? How to sample from an approximate distribution? If we don't have GBM, what should we do? Well, we have classical methods. We could approximate the valuation with a PDE, with finite elements or finite differences, and evaluate the solution along stochastic paths of the underlying. We could approximate conditional expectations with least squares regression. We could also go to so-called backward stochastic differential equations. I didn't touch upon those, but I saw that Matthias may do a little bit with the BSTEs. That can be also based on Monte Carlo. And even we can use Fourier-based techniques. Now, what we will do is the following. So this is our strategy. the strategy that worked in one paper for one option only, and now it is also generalized to multiple options in a portfolio. So at each exercise date, we would like to find a representation, boldface F, which goes from RD to 0, 1, yeah, where a 1 represents that it's optimal to exercise the derivative at time t, and the 0 says that it's suboptimal. So we would find, I will go in detail later, but we will have two stages. First, we just look for the early exercise decision. Yeah, so we would generate trajectories of the risk factors or the asset path. Risk factor and asset path, they are used interchangeably. And for each exercise date, we would evaluate that optimal stopping decision. Yeah? And based on that optimal stopping decision, we come up with a stopping time, tau star, which is the minimum for which ft is equal to 1 at a path. Yeah. And the distribution of a Bermudan exposure is then approximated by an empirical distribution created by many trajectories t. So we split it in two pieces. So if you think of my first lecture on Tuesday, we didn't, we had the constraint, or we had the early exercise payoff, and we had the continuation, and we used them, we combined them somehow. We combined them. And here we really separate two stages. We first look, where is it optimal to exercise? We flag the regions where it's optimal to exercise. And then in the second stage, we will look for the continuation values. So our aim in this work is to introduce a method capable of approximating the exposure profiles for a portfolio of high-dimensional and exotic derivatives. We have capital J derivatives. We have a risk factor X taking values in RD. Then we have curly T, and that is the space of all stopping times. Yeah, all stopping times vectors taking values T1, T2, etc. in 0 to T to the power J. So we look for the stopping times in our time frame for all of our vectors. For all of our risk factors, we have a stopping time, a set of stopping times, right? Yeah. Then the valuation of a portfolio, that is the supremum over the tau, the tau in the curly tau of the sum, J runs from 1 to J, of the expected value of the discounted payoff. Yeah, the discounted payoff up to the stopping time from T to TJ, to tau J. And the exposure at a state txt, that is given, the netted exposure is given as the maximum of the sum, J runs from 1 to J, of the exposures given that, given the early exercise decision. Yeah, the early exercise decision. Given tau is greater than T. And in the case of the non-netted exposure, it is the sum of the maximum. This tau 0j star is the stopping strategy that satisfies the expression above. Yeah. So, and that is this expression. E is not a Markov process, but E times the indicator function is in fact a Markov process. Now again, let's divide the problem into two sub-problems and solve each of these sub-problems separately. In phase 1, we use neural networks to learn the optimal stopping rule from Monte Carlo samples of the underlying risk factors. We just learn these zeros and ones, where 1 means it's optimal to stop, So it's optimal to exercise, and 0 means we continue with the option. And in phase 2, we apply the stopping rule from phase 1 on Monte Carlo samples from the underlying risk factors to generate cash flow paths. And we use neural networks to learn the mapping from the underlying risk factor to the exposure. So the cash flows are labels. We try to minimize the mean square error between our approximation and the cash flow paths. So this is a regression phase. And in other words, we use for the regression, we use also a neural network. We use 2 neural networks. We split the problem in 2 parts, and these 2 parts are relatively easy. Together, they are difficult. So to work with early exercise and to come up with a regression at the same time, that makes a complicated neural network. But chopping the whole problem in 2 pieces, we can come up with 2 robust neural networks that typically work and are not so sensitive to these hyperparameters. So phase 1 is a generalization of this deep optimal stopping algorithm. It's a well-known algorithm. It has been published in the Journal of Machine Learning Research in 2019. It's from Becker et al. It's called deep optimal stopping. And our presentation is based on 2 papers that have recently appeared, and both in Applied Mathematics and Computation, and they are also available on arXiv. One is called a deep learning approach for computations of exposure profiles for high-dimensional Bermudan options. And that is just looking at Bermudan options. And the second one is deep learning for CVA computations of large portfolios of financial derivatives. So that is the portfolio aspect. So the methodology, if you wish, the neural network methodology is presented here and tested here for some simple Bermudan options for which we have analytic solutions, for example, and for which we know a lot. And it's rolled out towards financial practice, looking at portfolios of financial derivatives here. And what I do here is I just give you an outline of these 2 papers, right? Let's look at phase 1, learning the optimal stopping policies. So again, for each derivative, little j, 1, 2, up until capital J, we have an early exercise region, an exercise region. So that is the region X in RD, where the value of the option or the exposure, the value of the option is equal to the payoff. Yeah? And T is in an early exercise time, right? And we have a continuation region, CJ, X in RD, where VJ is larger than the payoff, or T is not an early exercise point. And there can also be other points for which there's no early exercise possibility, then we have to continue. And in this particular case, we look at optimal decision functions, F star J, depending on T and X. And that's an indicator function that says X is in the exercise region. So it flags 1 when X is in the exercise region, and it flags 0. Otherwise, it's just a whole bunch of high-dimensional 0s and 1s. Yeah. And based on those, you can imagine we can come up with the stopping time. The first time we switch from a 0 to a 1, that could be the optimal stopping time for a specific X value. So we have an optimal decision vector consisting of capital J optimal decision functions. And these are, as I mentioned, these are multi-dimensional 0s and 1s. This is an example of continuation and exercise regions. Let's look carefully. This is two max options. The first one is a call and the second one is a put. And these would be, for example, some regions. This is the region where where we have continuation of 1 and continuation of option 2. That's the yellow region. Then we have the green region where it's exercising 1 and continuation in 2. Then we have the blue region, which is exercising in 2 and continuing in 1 and exercising in 2. And then we have the yellow region, which is overlapping here, and that is exercising in 1 and exercising in 2. So we get these nice arty works, but you see it is a difficult decision. We have zeros and ones. You can imagine the exercise region is flagged by a 1. And this is just for one time point. This is a projection in one time point. And we have multiple time points at which we make these 0 and 1 decision functions. Because only in the continuation region we need to come up with our continuation value. In the exercise regions, we know the solution. It is the value of exercising, right? The payoff. Here we have a second one. This is 3 regions even, just 3 options in our portfolio, just to show you that it can get increasingly complicated. We have the exercising continuation region for 3 options. The first 2 being a call and a put max option, and the third one being a geometric average call option. And then we get these pictures where we have all yellow is all of them continuing, and red is one of them exercised, and the other 2 continuing, etc., etc. This can be increasingly complicated, so you can imagine it makes sense to come up with a very structured way of determining vectors of zeros and ones. Here it's optimal to exercise option number J, and here it's not optimal to exercise option number J. For each time point, we can just store that very neatly, and we have a neural network learn those decisions. So we have these stopping times, and we do them in terms of these decision functions. So we have a set of exercise dates, the dates where at least one of the derivatives may be exercised, and that's T pi. It's the union of all T's. And we have the number of exercise dates, that's the number in T pi, and that would be N. We simplify the notation, but I don't want to dwell too much upon the details of the work. I just want to convey the message, basically. Yeah, so suppose there's no derivative exercised prior to little t, then the optimal exercise strategy, tau star n, is a sum times a product. Yeah, a sum times a product. And these are these indicator functions of zeros and ones. The sum makes sure that at each time we look carefully whether it's an exercise time or not. And the product makes sure that there's only one exercise time. So that there's only one exercise time. And remember, when f is equal to 1, it means exercise. And that makes that this is 1 minus f, that makes this 0. It's a complicated sum times a product. Summation part is over all possible exercise dates, and the product part is to make sure that each derivative is exercised only once. Now this tau n is an ft stopping time given by the deterministic function or vector f star. And the random variables, of course, they depend on xt and t, right? So we have the random variables xtn plus 1 up to xt capital N. And as I mentioned, it's a whole vector for each time point we have, depending on the risk factor value, we have a 0 or a 1. And particularly, we have a stopping time at time t0, tau 0. Now let t be in that interval capital Tn minus 1 Tn, and assume that no derivative has been exercised prior to or at little t. Then the portfolio values are given, pi are given by the sum, j runs from 1 to capital J, the number of derivatives, of the conditional expectation of the discount factor from t to tau star times the payoff function at tau star x tau star. Compare that to the standard formulation where the supremum is involved. The supremum is gone. Now we can approximate the portfolio value by a simple Monte Carlo. Now I have not yet explained how to obtain the optimal decision function. That is a neural network, and that I'll show in the next slide. It's a sequence of neural networks. In fact, for every time point, we have a neural network. So we use many neural networks nowadays. That is all possible these days. So for each time point, we replace the optimal decision function f star by a neural network. Fn with the neural network parameters, or with the neural network biases and weights, and we collectively call them theta tilde. Yeah, theta tilde. So it runs from RD to 0, 1. Yeah, we want to find the set of neural network weights and biases such that all these decision functions, all these decision functions are giving us, so all these neural network decision functions are good approximations of the true decision functions with zeros and ones. Yeah, that is what we want. And for each time point, we have a neural network. And we want they are learned, the neural networks are learned. We want the neural network weights and biases such that the loss function is minimized. And the loss function, we have a minus here because we typically minimize in neural networks. So we need a minus in order to stay in the methodology of the neural networks. And then we look at the expectation of the sum of exercising and the cash flow when we exercise. So exercising, these would be 1, f would be 1 if they exercise. So it's the sum of exercising times the cash flow plus 1 minus f times the discounted cash flow at a later time. So this is the cash flow when there's no exercise at Tn, and this is the cash flow when there is exercise at Tn. However, in general, we do not have access to the expected value here, so we approximate it by the sample mean, and unfortunately, Fn is discontinuous, right? Because we have these zeros and ones. If we would do it like this, these are either zeros or ones that we are looking for, and that makes gradient descent type algorithms unsuitable, and we have no access, moreover, we have no access to that T star at n plus 1. When we are at n, we do not yet know T star at n plus 1. And for each of these, we have a solution. For 2 and 3, we have a solution on the next slide. First solution is when we optimize in our neural network, we replace the discontinuous function with capital F, which is a continuous function, which runs between 0, 1, the interval 0, 1 to the j. And then after optimization, we set f to be discontinuous again. We make it discontinuous again with an operator alpha, script alpha, which is the component-wise round-off function. So alpha is 1 when xj is greater or equal to 1/2. So essentially, the neural network is learning a function between 0 and 1. And at the end, we round it off. When it's less than 1/2, we make it 0. When it's more than 1/2, we make it 1. And by this way, we can use gradient descent algorithms. We have a smooth function, in fact, that we are learning. Now, the other thing is that we don't know tau star at the new time point. The solution to that is that we go backward in time, right? At final time, we know. At final time, at maturity time, we know that f tilde should be 1 when the payoff is in the money, and it should be 0 otherwise, right? And if we have a final time which is somewhere in the middle, that can be when we're dealing with multiple contracts in our portfolio, then after that final time, all the weights or all the functions are equal to 0. Yeah. So at maturity of the portfolio, the optimal decision function is known, and we can set that. And then the optimization is carried out recursively backward in time. We know it at final time, we go backward in time. So we learn backward in time. Some details about the structure of the neural networks. So we have 1 up to 3 hidden layers. We have 15 up to 30 nodes per layer. We use a component-wise ReLU activation function in the hidden layers and a component-wise sigmoid function in the output layer. And that last part is to guarantee that the solution is mapped into 0, 1. We want an outcome into 0, 1 because that is our target solution. And for that, we use the sigmoid function. We have the Adam optimizer that we are using by Max Welling. And all the details, again, it goes a bit fast and it's very technical. Details are in the references, but I hope to convey the idea. And the idea, the general idea is if you use a neural network for numerical solutions, it's typically nice to include some user knowledge. And so not to give it the problem and let's solve it and let's wait forever, but to give it some components, like here we split the problem in two pieces that are relatively easy for a neural network. Before we also did similar things. So it's always to put in financial knowledge or numerical knowledge in order to help the neural network converge fast and reliably and not get stuck in a local optimum. So we sample M-train training samples. We make risk factors, XT training. We distribute them as X, right? And for all these derivatives in the portfolio and for all these samples, we compute the cash flow at final time, because that is the payoff at final time. Right? And then we go backwards in time. We look for the weights and biases in the neural network configurations, which approximate that what we have just seen. An average, this is the average as an approximation for the expectation of the sum over J derivatives of these functions that are smooth, capital F, that are smooth, the functions times immediate payoff, plus 1 minus the function times the cash flow at the later time point. So again, we look at immediate payoff versus continuation. And yeah, so for all J and for all M, we update the cash flow at a certain time point and we move backwards in time. Yeah, so we always need to look at the cash flow at a later time. And if we go backward in time, we have that computed already. And the other part is the cash flow that is generated by immediate payoff. And so then here, of course, the cash flow at a later time, that's a discounting cash flow. Yeah. So we sample M. This is the valuation. So this was the training. This was the training of the neural network. Then we have the valuation part of the neural network. We sample M-vol valuation samples. We denote the vector of optimal decisions by this. And then for sample M, in that valuation sample set, we have the following stopping rule. We look for the theta, which is tau of that F function that we have just computed with the neural network, and we make it like we did before, a sum times a product. Yeah, and then the estimated portfolio value at time t0, that is the portfolio, is again an average over the valuation times the sum of the discounted cash flows. So it looks difficult, but again, with the papers and with the deep optimal stopping paper at hand, it is possible to do it. We also did it. Phase 2 is we learn the portfolio exposures. So that is basically we learn a regression. So we have vectors. Let me see. Yeah, in terms of time, I'm still good. We have vectors for t in capital T n minus 1 Tn. We have vector valued discount processes, J of them, right? For the J values in the portfolio, it's the discount from T to tau star. And we use the tau star from before, but from stage 1. So we use the stopping rule from phase 1. Then we have a vector of discount values, a vector of payoff values for each of the j derivatives. And we have the product, this is just the component-wise product. So we have y, vector y, which is the component-wise product of the discounting and the payoff. And we have the early exercise process, the exercise process. So the indicator function that the early exercise time is before the final time. Then we look for regression, and we know regression, right? That is the arc min of a z. We try to find a z so that in expectation z minus zs, where zs is a square interval function, satisfies this in the 2 norm, right? We look for that, and let's recall the equations for the exposure. The netting is like this, where of course we have not yet exercised, and the usual exposure is like this. This is the max of the sum. This is the sum of the max, and then we look for the regression. We look for the values. So v t is in the arc min of z, of the expected value of z minus y squared in 2 norm, and we look for a sum of portfolio values where it has not yet been exercised. That's the arc min of z in a d-dimensional function. And we look for the expected value of z minus the sum of all these vectors squared. Yeah, so we look for a regression for the whole portfolio simultaneously. So given m regression samples distributed as x and little t in tnt, we define the following empirical regression problems. We look for a z that minimizes, so we look for a minimizer z for 1 over the number of samples times the sum of the samples of z minus yt, and we look for a z of the sum 1 over the number of regression samples of the sum of z minus the sum of j, yj, times the indicator squared. And the classical way to approximate regression is least squares Monte Carlo. Yeah, and one would search for functions in a smaller function class like polynomials up to degree 4 with the cross terms. The good news is then that you have a closed form solution when this D, where we look for our solution, is the class of linear combinations of polynomials. We often have a closed form solution. It overcomes the curse of dimensionality. However, one may run into memory issues. And the drawbacks for least squares Monte Carlo is it's not so easy to choose the basis functions yourself, especially when the function surface is complicated. And it's also not trivial to approximate a vector valued function. Yeah, so it's not so easy to approximate a vector valued function. Here you see we approximate a vector valued function, and here we do it as a sum of components. So again, our solution for this stage 2 is to use a neural network based regression. So we let calligraph D be the class of functions which can be represented by a neural network with all the hyperparameters specified. So we let the neural network search our basis functions essentially. Yeah, so we can optimize the parameters in the neural network to approximate the regression 1 or the regression 2. And so the good news is it's possible to specify larger function classes without running out of memory. There's no need to specify clever basis functions because, well, the neural network should find it itself. Unfortunately, there's no closed form for the optimization problem. It is a black box, and that is a disadvantage, of course. And it's also a little bit more time consuming than the least squares Monte Carlo setting. So in summary, in our experience, for only one derivative, J is equal to 1, and a low-dimensional risk factor X, and a relatively simple payoff, the least squares Monte Carlo is to prefer. But if we have multiple derivatives in a portfolio, a high-dimensional risk factor, and a complicated payoff, then the neural network-based regression appears to be more accurate. So we use neural networks, Z n of psi n, and we use empirical loss functions. So we try to minimize the vector valued or the component-wise one. So we look for a Z so that the regression is optimal, is minimized. And also we do that in this case. So that is basically stage 2. And we use essentially the same neural networks that we used before. There's one little difference. Of course, we don't need to end up in 0, 1. So our final activation function is not a sigmoid anymore because we don't need to land in 0, 1. Okay, 2 numerical experiments to finish this 10 hours of lectures. I'll start with the Bermudan option on the Black-Scholes dynamics. So the only risk factor here is the d-dimensional asset price process with components 1, 2 up to d. So that is the risk factor. It's S, the stock under Black-Scholes. So S0 e to the power r minus q, q a dividend, minus 1/2 sigma I squared t plus sigma I omega. So we here we assume no correlation, but it doesn't, oh yeah, they are correlated, sorry, they are correlated. But sometimes we assume no correlation, but it doesn't matter. It's just for model situations because we have done a lot of experiments in the paper with correlated Brownian motions. A max call, as a payoff, it has the maximum of d stocks minus k and 0. The arithmetic average option, as payoff, it has 1 over the sum of stocks minus k and 0, the maximum of this expression and 0. And the geometric average option, for which we have an analytic solution, as you know, I told you on Tuesday, it's the product of stock values, the product of d stocks to the power 1 over d minus k, and then this expression and 0, the maximum over that is the payoff of this one. So here we consider in the first experiment a portfolio of put and call options, Bermudan max options, arithmetic average option, geometric average option, and 10 exercise dates. And we look at the values. So we have a reference for the max option, put and call from a paper, 13,902. And for the put 9.530, we don't have a reference value for the arithmetic and the geometric option. In this case, it's early exercise, Bermudan option, then it may be difficult. The deep optimal stopping, so our deep optimal stopping variant, well, it has very good coinciding values for the references. You see 13.9, 13.899, 9.53 and 9.528. SGBM from last time, it is a little bit too high, and also here a little bit too high. And LSMC, the Longstaff-Schwarz least squares Monte Carlo, it's a little bit too low. Now these methods, these Monte Carlo methods, let's think about it. They have typically been used to determine the option value of a Bermudan option. And the option value is the value at T0. Here, however, we do not only look at the option value at T0, we look at exposure over time. So we look also at later time points. We want to have a good representation of the option value of the early exercise regions and the continuation regions. Well, for all of these computations, the Monte Carlo methods are a little bit worse, but not that much, of course, but a little bit worse. And the deep optimal stopping appears superior. And when we expect them all to be the same, it gives us confidence that the deep optimal stopping is actually doing a pretty good job. These results are with 5 runs. In LSMC and SGBM, each derivative value is computed individually because we cannot do it otherwise. But for the deep optimal stopping, they are all computed in one run. We can look at the whole portfolio and come up with the exposure profiles in one run only. An expensive run with 2 stages and neural networks, but it's one run. Well, here we see the early exercise regions for a 2-dimensional max call at a certain time point. And here we have a reference solution, which is computed by finite elements, an American option. It's a 2-dimensional one, so that's still possible. And this is our exercise region, the red one, and the black one is the continuation region. And our approximation of this with the neural network is pretty accurate. This is the neural network solution. And you see that also at this intermediate time point, the early exercise regions are pretty accurate. The continuation regions, the early exercise regions. In SGBM, in our setting, it is a little worse. We see a wiggly pattern. It's only a minor problem, but this is due to the bundling. If we use bundling, we see the effect of bundling on these early exercise regions. And Longstaff-Schwartz also has some strange phenomena over here. It is not perfect. And in many ways, this neural network setting appears to be robust. It appears to be accurate. And it's a good alternative, right? The disadvantage is, of course, that we have no proof of convergence. But, well, you know, you can also think, how good is your proof in the Monte Carlo setting? So for this problem, we also have the expected exposure, the potential future exposure at 97.5% and at 0.25%. And we compare them we have 2 different regression techniques here, and we compare the results and we see very similar results. So this is neural network-based regression. We see that these results are very similar. Now we finish off with the Bermudan swaption on the Hull-White dynamics. We have not discussed it at all, but it's still interesting to see what we can do. In this example, we have a portfolio of 6 Bermudan interest rate swaptions with partially overlapping exercise dates and different strike prices. And we compute the values with the expected exposure, the potential future exposure, and the potential future exposure at 0.25%. And we compare it with SGBM. And we see very accurate results. They overlap more or less, but SGBM does this individually for each derivative. And we do it for the whole set. And we see that the PFE goes up first drastically and then goes down. But this is for 6 different swaptions. So that's pretty nice. And the blue one is the expected exposure. So this concludes my talk, ladies and gentlemen. So this is the problem of exposure computation. I know it's technical. But I want to convey the message. It's technical. Sometimes it's technical in numerical techniques, right? And especially with these neural networks, we are also facing the question like, how good is this, right? We see that it is good, but how can we prove this? The problem of exposure computations in the context of valuation adjustment is now cast in the neural network setting. Yeah, we have 2 stages. We detect early exercise regions and optimal stopping times with, we also have the neural network regression, and we come up with a robust framework. It's not so sensitive to the specific choice of the neural network hyperparameters. If we have one hidden layer more or a few neurons more or a learning rate a little differently, it converges. By splitting it into 2 pieces, we make it a robust setting. And I think it's an interesting approach when dealing with portfolios of financial derivatives. And that concludes my 10 hours. So I thank you for all your attention. And I wish you good luck with Matthias Erhardt in the afternoon and